Now students, in this particular lecture we will be seeing some few more questions which has appeared in your 2021 ATC examination in physics subject. So the very first question here we will be discussing is a galvanometer coil has resistance 20 ohm and the meter shows full scale deflection for a current of 2 milliampere. Okay, so full scale deflection for a current of 2 milliampere. Okay, how will you convert the meter into an ammeter of range 0 to 6 ampere? See, this is a very good quality of question first of all. Okay, and students generally get confused that whether the shunt resistance has to be connected in parallel or series. Okay, first of all, we will see the theory before it. I had already completed the lectures, but still for our other viewers who are not our paid users, I should simply elaborate a simple theory related to that. So first of all, how exactly we will approach that? In the lecture, I had told about ammeter. I had told that this is actually a low resistance device. This ammeter is actually a low resistance device, and because we have to convert that galvanometer into an ammeter, so our agenda is that whatever the galvanometer is there, it should at least have a full scale deflection for a current of 2 milliampere, right? So that should not be hampered. This thing should not be hampered. So what we will be doing, suppose I'm just taking an example right now, that suppose this is our galvanometer. Okay, this is our galvanometer. Suppose this is positive terminal and this is negative terminal, and it has been mentioned that it is having a resistance of 20 ohm, right? Now, because we have to convert this into an ammeter and it is having a full scale deflection of current 2 ampere, so this cannot be changed. Whatever the 2 milliampere full deflection is there, that should at least go to this galvanometer. Okay, so this Ig, I am representing that 2 milliampere as Ig, but I want that this galvanometer should work as an ammeter. So see very carefully, it is very important right now. So what I am doing, suppose from here, suppose from here 6 ampere current is coming, right? But this galvanometer is having full scale deflection for a current of 2 milliampere only. So rest of the current should go somewhere else. But if we will connect, if because we have to connect a shunt resistor. Okay, so now to just define the position of that shunt resistor, we will think about that where exactly we should place that. Whether I should place it in the series with the galvanometer or with the parallel with the galvanometer. Then I come to know that in series the current actually remains same. So if the 6 ampere is there, if I should connect a shunt resistance, then what will happen? The current will remain same. The current will remain same in both galvanometer and shunt resistance, but this galvanometer is having the full scale deflection for a current of 2 milliampere only, and this 6 ampere is much larger than this full scale deflection of the galvanometer. That's why we will thought that we have to divide this current, and to divide this current always you have to prefer a parallel connection, because in parallel connection only what happens, the current actually gets divided. So this shunt resistance we actually connect in parallel. Sir, in the question it is given that it should be connected in series. See, the answer is wrong here. In this particular question, ATC had given a wrong answer and I had personally claimed this particular question. Okay, and for this particular question, the student had actually got a bonus mark, and even like after normalization they were having a very good advantage. So this question was not identified earlier that it should have it or it has to be like claimed, but later on when I had solved Each and every question I found that this question has to be claimed, and I had claimed this particular question that time. Okay, even previously I had posted the questions related to probability. You will not believe, in many other teachers has claimed those questions also. Okay, so I'm frankly telling you those questions were exactly correct, but this question was wrong. Okay, so that shunt resistance has to be placed parallel to this, then only the remaining current will pass through this shunt resistance. Okay, so if Ig is going here, so this is, suppose this is I, so this way it will be I minus Ig, and right now only you can see this is 6 ampere, this is 2 milliampere, this 2 milliampere is nothing in front of this 6 ampere. So what you can do, you can even ignore this Ig. Whatever the current is there, it will go to the shunt resistance, you can simply imagine. Okay, so when you had connected this, whenever you had connected this, it, because the shunt resistance is in parallel with the galvanometer, and in parallel what is same, what remains constant, actually the voltage across shunt resistance. This is your shunt resistance, so shunt resistance will be same as the voltage of galvanometer. Okay, so voltage is simply given by V is equal to IR, right? So voltage is like this. So here in shunt resistance, for shunt resistance current we are considering as I, we are neglecting this Ig. Okay, so I into R resistance, this we have to actually calculate. The shunt resistance has to be calculated because it has been given in the question, and even in the theory I had told you, even if you have to convert that into voltmeter, you have to actually place a shunt resistor in series. Okay, but here in case of like conversion of a galvanometer into an ammeter, you have to place the shunt resistor in parallel. Okay, so I into Rs. Okay, this particular voltage will be same exactly to the voltage of this galvanometer. So along the galvanometer the current is Ig, right? And the resistance of galvanometer, it has been given, that is 20 ohms. Okay, so from here you can very easily calculate the value of Rs, and Ig, it has been mentioned as 2 milliampere. So 2 into 10 to the power minus 3 into 20 divided by this I has been given as 6 ampere, so it is 6. Okay, so by default I am telling you this is directly like solvable, very easy question. This is 10 times, this is 3, 10 into 2 it is 20, 20 divided by 3 into 10 to the power minus 3, 10 to the power minus 3 ohm can be written as milli ohm, and 20 by 3 it can be written as 6.67 into, or 6.67 milli ohm. So answer they had given correct, answer was exactly correct. Okay, but the correction has to be done here, and the actual answer should be D. And later on, like this question might have got corrected and student were benefited from this. Okay, I hope you might have got the concept which I had told you, and rest for the detail you can simply refer. I think of 20 minutes I had taken the lecture for this particular topic. You can simply learn from there. Now next question. E1 is or sorry, this diagram has been given, and from the question as I can see, it is a large charged plate. Okay, they had asked like this is electric field, volt per meter, it is electric field. So this side electric field is different, this side the electric field is different. Okay, so and you might be knowing whatever the external electric field is there, it is same everywhere, but because of this placement of this charged plate, the electric field actually gets changed on both of the sides. Okay, this is the actual scenario that I had already covered in the video lecture. Okay, so what will be the charge density on the plate in SI units? Charge density on the plate. So charge density on the plate is represented by sigma according to our theory, according to our video lectures which we had covered. The electric field on two sides of the charge plate is shown in the figure. E naught is the permittivity of the free space in the SI unit. So they had told you to calculate this. See, first of all, this question is really very good. Why it is very good, I will tell you, because somewhere this question is incomplete. Because in this particular question, they had not mentioned that whether the outer electric field, which is actually remains constant everywhere, okay, or you can say the external electric field. See, here there will be two kind of electric field: external electric field and electric field due to this large plate. Okay, so they had not told at least, or even they had not even given you some hint that which one is larger or which one has to be considered as larger one. Okay, so that's why we have to understand ourselves that which has to be considered accordingly. So what we had done, okay sir, this side it is E1. So as you can see, this is somewhere lesser. So what will happen? E1, I'm simply considering, suppose this external one is E naught. Suppose this external one is E naught, and the electric field, because of this large plate or large charged plate, that is suppose E. Okay, so this E1, because this is lesser, so from E naught something has to be subtracted. Okay, and E2 something has to be added, then only this will be appeared. See here, what I had considered that E naught is larger. This is my assumption. What I had done, this was my assumption. I had considered the external electric force larger as compared to the electric field because of this large charged plate. Okay, now next important thing, if we are considering this one, so what I will be doing, sir, simply replace the values and let us calculate the things. So what I had done, I had simply replaced it. This will become 14, this will become 18. When I had added, this was simply got cancelled, and E naught will be like it is 14 plus 18, it will be 32, 32 divided by 2, it will be 16 volt per meter. Okay, so we had calculated E naught. E naught means the external electric field. Okay, then by default, the electric field due to large charged plate, that will become 2 volt per meter. Okay, and one very important thing, the electric field due to large charged plate in terms of charge density, it is nothing, it is sigma upon 2 epsilon naught. Epsilon naught is permittivity of free space, right? So from here, like, you have to calculate this sigma. Sigma is nothing, it is E into twice E naught. Okay, so by default, if E is 2, so 2 into 2 E naught, that will be equal to 4 E naught. That is our answer. That means our assumption was correct. Our assumption was correct that external electric field is larger as compared to that. Sir, what will happen if we are considering that the electric field because of this large charge plate is greater? In that case, what will happen? I could show you. Okay, in that case, what will happen? I could tell you right now. Suppose this 14 will be equal to E minus E naught. In that case, this will only happen, or E plus E naught, right? So when we will be adding, E naught and E naught will get cancelled out, and E will be like 16 volt. Sorry, E will be 16 volt per meter, and E naught will be 2 volt per meter. And E we had assumed as E, sir, it is the electric field due to large plate. So at that time, this E into twice E naught, that will be 16 into twice E naught, and that is 32 E naught, and that is not mentioned in your option. So if that is not mentioned in your option, in that case, what will happen? You have to at least assume that which electric field you have to consider as large. I was having enough practice. I was very easily able to check here that which one is larger. Okay, that's why I had proceeded in the same format, but at least you have to do this particular thing into the examination also. And even I had told various tricks to like directly attempt such question. Okay, now next question. Light with an energy flux of 18 watt per centimeter square falls on a non-reflective, see this is non-reflective surface. So what is the use of non-reflective or for complete absorption? That is the meaning of non-reflecting surface. That means whatever the light is falling on that surface, the whole energy is getting absorbed, or the whole momentum is getting absorbed inside that. That means the final momentum of the light is actually zero, right? If the surface has an area of 20 centimeters square, find the total momentum delivered. So total momentum delivered during a 30-minute time span. See, first of all, this has been given, the power factor has been actually given to you, that actually the light with an energy flux of this 18 watt per centimeter square. Okay, so first of all, what I will be doing, I will be calculating. See, first of all, how you will be calculating the total momentum. See, the rate of change of momentum is force, and even for total energy, even I had told you that force into velocity is actually given by that energy. That energy is actually the final answer, right? Sorry, power will be your final answer. So in that case, I am simply telling you here, this is power. So power is what? Sir, power is nothing. Power is energy per unit time. And this force, I can write this force as the rate of change of momentum. Rate is also defined with respect to time. Okay, so this is momentum, the rate of change of momentum, P by T. So that's why T and T will get cancelled out, and directly you will be getting E is equal to P into V. So this thing I had taught you specially for the solar panels. Okay, in our video lecture, this thing I had taught you for the solar panel. You can directly calculate that what is the exact momentum transferred, or what is the energy transferred if momentum has been given in the question. This I had already told you. So just for other student, I had represented this formula once again. Okay, so for this you have to calculate this energy first. This is total energy. So total energy will be, sir, this is per centimeter square. So total area is this one. So first of all, calculate the power usage per second on the non-reflective surface. Okay, so 18 into 20. This was, I could simply write all the units also, then it will be more feasible for you. Okay, this is 18 watt per centimeter square into 20 centimeter square. This is the power consumption per second inside the whole surface. But we have to calculate the total energy consumption. We are calculating energy, we are not calculating power, right? So that's why we will be multiplying by time. So that time is given as 30 minutes. So 30 minutes will be total 30 into 60 seconds, right? So by default, this watt is simply written as joule per second, and second will get cancelled out, only joule will remain. So overall, whatever your answer will be there, it will be in joules. Okay, centimeter square will get cancelled out, and watt into second, it will be joule. Okay, so this will be 6 into 3, it will be 18 into 2, 36 into I had made some mistake. This is 18 into 20. Okay, this will be 360 into, this will be 1800. Okay, so directly you can calculate the whole energy. Okay, now next important thing, you have to actually calculate the momentum, total momentum delivered. Okay, so total momentum delivered, P, from here you can directly calculate P total will be equal to E total divided by velocity of that particle. Here that particle is light, so here we have to we will write the velocity of light. That is very important. So P total will be equal to E total. E total is 360 into 1800, this much joules, divided by velocity of light, it is 3 into 10 to the power 8 meter per second. So joule second per meter, it is also kg meter per second. Okay, when you will be calculating, it will become kg meter per second. Very easily you can even calculate that. Okay, so from here what you will see, sir, here we will be seeing that it will become 600, and this 10 and this 20, it will simply get cancelled out. Okay, if it will get cancelled out, then this will simply become 10 to the power 5. Okay, this will become 10 to the power 5. Okay, and 36 into 6, it will be 216 into 10 to the power minus 5. But here the answer, the constant is 2.16. So for 2.16, it will become 10 to the power minus 3 kg meter per second. So everything has been verified. So the correct answer will be C, 2.16 into 10 to the power minus 3 kg meter per second. So I hope you got a broader idea that how exactly we are approaching the question, and with due practice you will be very easily able to answer all the questions. Even I bet you out of 30 questions, physics, okay, even with a general introductory video lectures, I bet you that you will be able to solve 28 out of 30. For rest of the two questions, you have to do even more practice. But with the video lectures which I had given you, these many questions will be very easily done. Okay, with the assignment questions. At least do the assignment questions also, which I actually give after the video lectures. I hope you got the things. In the very next video, we will be solving some more previous year question with a very great depth. Let us see.